Welcome grade 12s to STEM in Action's Boost series. I'm Taryn Roberts and we'll be looking at part 2 of electrodynamics. So if we have a look at the section or topic of electrodynamics in your syllabus, there are two sections, electrical machines and alternating current. In part 1, we looked at AC and DC generators, and now in part 2, we will be considering motors as electrical machines, and we will be investigating or exploring AC and DC motors. But first things first, let's consider the pre-knowledge required to understand AC and DC motors. So in grade 11, we considered current-carrying conductors, and we realized that there is a magnetic field associated around a current-carrying conductor. So if we have current, we have an associated magnetic field. We can use the right-hand wire rule to determine the direction of that magnetic field. So we use our right hand, and our thumb would point in the direction of the current, and our fingers would curl in the direction of the magnetic field. And you can see that in the diagram over there. Let's see how this works. Once there's no current, there's no deflection of the compass needle. The minute we have current flowing through the wire, there's a deflection of the compass needle indicating a magnetic field associated with that. And again, our thumb points in the direction of current from positive to negative, and our fingers curl in the direction of the magnetic field. Let's consider a solenoid. We also covered a solenoid in grade 11. So if we take a straight wire and we start coiling it, it is called a solenoid. Again, that wire, once it carries current, it has an associated magnetic field around that solenoid. We again can use a right-hand rule, but in this case, it is a right-hand solenoid rule. Now, the fingers would curl in the direction of the current from positive to negative, and our thumb would show the direction of magnetic field, and our thumb would point to north. So you can clearly see in that diagram over there, we have got a solenoid, as we've got wire curled around a metal core. We've got a current from positive to negative, and so I take my fingers and I point them in the direction of the current, and my thumb points downwards, pointing to north, and you can see on the right-hand side, the application of the right-hand solenoid rule, fingers curling in the direction of the magnetic field, and my thumb automatically points to North Pole, indicating the direction of the magnetic field. We also know that a current-carrying conductor moving in a magnetic field induces an EMF. So there's a change in magnetic flux linkage, and this can be brought about either by moving the conductor in and out of the magnetic field, or keeping the conductor stationary and moving the magnet over the conductor. Both of these situations bring about a change in magnetic flux linkage, and this induces an EMF. We also need to know Faraday's law, and this states that the EMF induced around a single loop of conductor is proportional to the rate of change of the magnetic flux through the area of the loop. This can be written as mathematically: the EMF, or the induced EMF in a conductor, equals minus N delta phi divided by delta T, where phi indicates the magnetic flux, and that formula, if you can remember, is given by the magnetic field multiplied by the area of the coil times cos theta. B, as I've said, is the symbol for magnetic field strength, and the negative, also N, is the number of turns in the coil, and that negative indicates that the induced EMF opposes the change in magnetic flux. This brings us to motors, which is the example of an electrical machine. Motors are devices that convert electrical energy to mechanical energy. If you can remember from part 1, where we considered generators, we were converting mechanical energy to electrical energy. It's based on the principle of the motor effect, and in this case for motors, we use Fleming's left-hand motor rule to determine the direction of rotation. When we covered generators, we had a magnetic field, and we had a manual rotation. So we had force and we had magnetic field. And those two together gave us an induced current. That was for generators. For motors, on the other hand, we do have current because we have electrical current converted to mechanical. So we've got current, we've got a magnetic field, and those two together give us a rotation force or a moment of rotation, a torque. We can use Fleming's left-hand motor rule to determine the direction of this rotation. So let's look at the motor effect and motors. If we have a look there, we know that this is a motor, number one, because we have a power source. In this case, we just have a little cell over there. The cell is attached to the coil, and since that coil is in a magnetic field and there's current flowing through the coil, we have a rotation force that is being generated. So we have a force of rotation or a moment of rotation, or what we call torque. For motors, the current carrying coil is placed in a magnetic field and it has to have an AC or DC power source. Both sides of the coil experiences a force on either side, and that creates the torque that we can see as that coil rotates over there. It makes a turn, and we can use Fleming's left-hand motor rule to determine the direction of that rotation. So let's have a look at Fleming's left-hand motor rule. Of course, we use our left hand. And in the case of generators, we use the same fingers or same digits. We've got father, the force, at right angles to mother, the direction of the magnetic field. And then they have a child, and this second finger gives us the direction of the current. In the case of motors, we will have the current direction, we'll have the magnetic field direction, and those together will give us a force of rotation, and so we will be looking for the direction of the thumb. I just want to remind you, in part 1, when we covered generators, we used the right-hand Fleming rule. In this case, we had the force because we were rotating the coil. We then placed that coil in a magnetic field, so we had the direction of the magnetic field. And these digits perpendicular to each other gave rise to C, the direction of the induced current. So that's Fleming's right-hand generator rule. We generate the right answers. And then here I like to use the term, he motored off and left. So I use my left-hand rule for motors. Very important. They will give us the direction of, in this case, the direction of rotation. So if we take a conductor and place it in a magnetic field, and that conductor is carrying current, it will move, they will move relative to each other. There's a force that is created or generated on both sides of the coil, and as those forces generate on both sides of the coil starts rotating. We can determine the direction of this rotation using Fleming's left-hand rule, and as I've said, my first finger will give me the direction from north to south, or the magnetic field. My second finger will give me the direction of the current, since I have a power source, and my thumb will point in the direction of rotation. And I also said that I like to use this little tip for recall. They motored off and left, so I use my left hand for motors. In the same way that we need to determine, or we need to identify or know the components of generators, we also need to know the components of motors. So let's have a look at the components of an AC motor. Over here we can see we've got a set of magnets that generates our magnetic field. We then have a coil, our brown component there, that's our coil or our armature that's able to move freely in that magnetic field. And then very important for AC motors, we have got two slip rings over there. And remember those two wedding rings that get slipped on the man and the woman's fingers? We've got two slip rings, and that's key. The key component for AC motors. They are connected to the armature via little brushes, and there we have our source. Please note, and we'll look more into this in part 3, but that is the symbol for a power source. It does not look like a cell or a battery. It has a little sling or sine curve. This is the symbol for an AC power source. So two things. I have a power source, which means I'm looking at a motor. I've got two slip rings, which means I'm looking at an AC motor. So these are very key for the components for AC motors. Let's have a look at DC motors. Again, we need a magnetic field. So we have two magnets. We need a coil, and there we are. It's placed in that magnetic field. We need a power source. Look at that power source. There's our familiar positive terminal and negative terminal, which in this case, I just have one cell. Mostly, I'll probably have a battery, a collection of cells. And then key. It's a motor, but it's a DC motor. Do you recognize the little hamburger without the patty? There we've got a split ring commutator. That black section there is the blank spot, the empty space where our patty would be. And remember, grade 12s, you cannot talk about hamburgers and wedding rings. These are study techniques that allow you to recall what a split ring commutator looks like and what slip rings are and in which motor they are found in, etc., etc. So there we are. We've now looked at the components of both an AC and a DC motor. Right, grade 12s. If we have a look at that, we recognize a set of magnets. We also recognize a coil in the horizontal position. And this is starting to look very much like a generator, but let's continue exploring. There we've got a split ring commutator, so it could still be a generator. But the key factor is that I now have a power source. I've got a cell, a positive and a negative terminal. The mere fact that I've got electrical energy tells me that we've got a motor. And I know that it's a motor because this electrical energy is going to be converted to mechanical energy. And the evidence of the mechanical energy is that that coil starts rotating in a magnetic field. In this case, the power source is direct current. So the torque is indicated as this graph in one direction as we have it over there. So we can see this coil rotating, and we can see when is the rotation a maximum. Let's go and have a pause. So we can see when this graph, let's go and see if we can turn it backwards. Okay, there we've got our coil in the vertical position. So we've got our magnetic field from north to south running longitudinally or vertically. And if we look at our coil over there, it's in a vertical position. If we look at the area of the coil and I draw a normal to that area, the normal cuts the magnetic field perpendicularly. In this orientation of the coil, we have a maximum force of rotation. As this coil continues rotating and gets to the horizontal position, I can see that the coil is now in a horizontal position. The area, if I draw a normal from the area of the coil perpendicularly, that normal is parallel to the magnetic field. In this orientation, our torque is at a minimum. Grade 12s, you need to know what is the orientation, either in terms of the coil, the frame of the coil, or the area of the coil. And if you understand what they're talking about, the question will lead you as to which aspects of the armature you need to consider to determine when is the turning force a maximum or when is the turning force a minimum. Let's have a look at another animation to explore the torque on a coil. So in this animation, we have a motor. How do I know that we have a motor? Well, it could be a generator because I've got a set of magnets, which I have in generators. I have a coil, which we have in generators. But the key point here is I've got a positive and a negative terminal indicating that we have a power source. So I'm going to activate that we can see the magnetic field, the direction of magnetic field. I'm going to show, let's see the current, the direction of the current in the coil. And we are going to look at how the torque on this coil changes as the coil rotates in the magnetic field. So let's run the animation. So you can see the size of that, the force of rotation. It's a maximum. So once that coil is in the horizontal position, the torque is at a maximum. The minute the coil is at a vertical position, we actually have the force of rotation at a minimum. You can see that this motor over here is a DC motor because we can clearly see the split ring commutator. So the force was at a maximum when the coil was in the horizontal position and the area was perpendicular to the magnetic field. And we could see the minute that coil was in this vertical position, the force, you couldn't actually see the force because the force was at a minimum. So when the coil was in a vertical position, the area was parallel. The area of the coil was parallel to the magnetic field, or if we drew a normal to that area, it would be parallel to the magnetic field. In that orientation, the force of rotation would be at a minimum. So how can we improve the efficiency of motors? Let's remind you again of what a motor is. We've got a coil in a magnetic field connected to a power source, and once we have that, we will have a force of rotation on both sides of the coil, and that coil will start rotating. The minute we open the circuit and disconnect the coil will stop rotating. So how do we improve the efficiency of a motor? Well, first things first, we could increase the current that passes through the coil. We could increase the magnetic field strength by using stronger magnets. We could increase the number of turns on the armature. And we could also increase the area of the coil. Let's look at some of the uses of motors in everyday life or in industry. I think for housewives, and I'm speaking about myself now, and I'm really actually hoping that you are those responsible high schoolers that are also doing chores around the house. This is preparing you for life beyond high school and life as a student. You will definitely start having to do chores for yourself. So when we're looking at our washing machines, our microwaves, vacuum cleaners, or even fans in summer, they make use of motors. Our windscreen wipers and our automatic windows, they make use of motors. And even our roller doors, the garage doors opening and closing, or our electric gates opening and closing, they all make use of motors, where there is a power source, there's a coil in a magnetic field, and because we have that, using the motor effect, it will generate a torque on that coil, which will show as a rotation. Let's have a look at our application of motors, AC and DC, by considering paper 1, March 2018, question 10.1. And it reads, learners want to build a small DC motor as a project. Important, we're now dealing with the section on motors, and which kind? A DC motor. Write down 3 essential components that are needed for the building of the motor. We only need 3 essential components, but I'm going to list as many as we can think of. But of course, the examiners will only mark the first 3. So if we think back on a motor, we are now taking electrical energy and converting it to mechanical energy. So what do we need? As per usual, so we're looking at 10.1. We need a coil or an armature. We need permanent magnets, which gives us our magnetic field. It is a motor, which means we have an electrical input, so we need a power source. And it is a DC motor, so we need a split ring commutator, and those connect to the coil via brushes. So grade 12s, for this to be a DC motor, you would have to list 3 essential components. I've listed as many as I could. I would definitely encourage you to have a power source and a split ring commutator, because both those components are found in motors and not in generators. And then the split ring commutator is found in a DC motor. And then of course you can select, and then another good one would be that you need to have a coil in that magnetic field. So I've listed more than 3, but for this question you only need to list 3 essential components to build a DC motor in the project. So let's have a look at another question. We are going to consider paper 1, September 2014, and we're going to look at questions 8.1 through to 8.5. Let's begin. The simplified sketch below represents a DC motor. So that tells us exactly which section of our topic we are covering. Name the principle on which the motor operates. So for 8.1, we know that motors are based on the motor effect. State the energy conversions which takes place in a DC motor. For a motor, we have electrical energy, and that is being converted to mechanical energy. This will lead to a rotation of the coil in the magnetic field. 8.3, give a reason why section BC in the above diagram does not experience a magnetic force while the coil is in the position as shown. And we will say it doesn't experience a magnetic force because BC is parallel to the magnetic field. 8.4. So we need to determine whether this coil is being rotated clockwise or anti-clockwise. We're going to use our left-hand motor rule, father, mother, child, force, rotational force, direction of the magnetic field, it's pointing to north, and the direction of the current from positive to negative. So if I look at my diagram, I've got north, the north pole, or the north to south, that's the direction of my magnetic field. My current, if I look at my current, I've got positive going through, and I'm going from A to B over there. So that's the direction of my current. So I can point my current towards you. I'm considering section A, B of the coil. So all my current and magnetic field directions are on the portion of AB of the coil. So I've got my direction of the magnetic field from north to south. I've got current from positive to negative. It's going from A through to B. And where is my thumb point? AB is moving down. So if I take my coil and this is AB, AB is moving down. If I rotate it, that's anti-clockwise. So just by using Fleming's left-hand rule, we could determine the direction of rotation. And in this case, it is anti-clockwise. 8.5. Write down one way in which the turning effect or the torque can be increased. Of course, we only need one, but let's list a few. It's a motor, so we could increase the current. We could increase the magnetic field strength. We could increase the number of turns on the coil. We could also increase the area of the coil. Those are just a few ways where we could increase or improve the efficiency of this motor. We only need to use one. I've listed more than one, so your examiner would only mark the first one. They'll not choose which ones they want. They'll mark the first one and stop marking. It is worth one mark, but for this segment, I've listed a few. So grade 12s, this brings us to the end of our second application on motors. It shows you how the topic or the content in AC/DC motors can be examined in a question paper or two. I do encourage you to tackle more generator and motor questions in your paper 1 which you can find a selection of in your Boost Prep Pack. So this brings us to the end of part 1 in electrodynamics, where we covered both AC and DC motors.